Well, good evening, everyone, and welcome to this public lecture. My name is Susan Pond. I'm the Director of the Australian Institute for Nanoscale Science and Technology, which is headquartered in this building. And of course, we're amongst an array of quantum research here in the research wing of the building. It's my pleasure tonight to introduce Andrea Morello. My phone has just decided I needed to enter my code again. Andrea, as most of you would know from the flyers put out for this public lecture, is Professor of Quantum Engineering at the University of New South Wales, Sydney, and a Program Manager in the ARC Centre of Excellence for Quantum Computation and Communication Technology. He's a Fellow of the Royal Society of New South Wales and a Fellow of the American Physical Society. He completed his PhD in the birthplace of low temperature physics, and I assume you'll be talking about that tonight.
Yep,
and
definitely.
Followed by a postdoc at the University of British Columbia in Vancouver, and joined the University of New South Wales in late 2006. If you go to the Spin Qubit with a Q3 website, you'll find the rest of his bio, which I'm not going to read out because we really do want to hear him speak tonight and allow plenty of time for questions on the subject of Schrödinger's cat is alive and means business.
Thank you very much. Thank you for the very kind introduction, and also for hosting us in this beautiful venue at the Australian Institute of Nanoscience and Technology. So we have the room for about an hour and a half. I will speak for probably an hour. I have a bad habit of going over time, but hopefully I won't bore you too much. I strongly encourage questions, but just to facilitate the narrative, I will ask that you keep them for the end. So today I will tell you about the challenges and opportunities and directions in quantum technologies. And my public lecture, or show if you prefer, will be divided in two parts. One is really one of my personal crusades about the way to describe quantum mechanics as something weird and counterintuitive and spooky. And people love to quote, Richard Feynman, who is attributed to him to say, if you think you understand quantum mechanics, you don't understand quantum mechanics. It's not actually quite sure if he really said that, but everybody likes to believe that. And my attitude to this is, well, speak for yourself, mate, because nowadays we have an understanding of quantum science that is far beyond what used to be even just 20 years ago, okay? So all the quotes you hear from the great geniuses of the history of science, they're great for a while, but they actually are becoming obsolete. So I'll spend some time talking about that, and then in the second part of the talk, I will show you how we make these things work for new technologies and also new businesses. So let me start by laying the foundation. What is actually quantum? You say quantum this, quantum that. You see, the quantum dishwashing tablets. You see quantum, property management, if you want. So what is actually quantum? So quantum is the description of the world that is most accurate as far as we know. And really, when you say that a system is quantum mechanical, what that means is that it's a system where the Heisenberg uncertainty principle matters. The Heisenberg uncertainty principle is really a law of nature that says that if you're trying to observe the position and the momentum, which is the mass times the velocity of some object, you cannot do that with absolute precision. This is not a statement about how good your measurement instruments are. This is a law of nature. The product of the uncertainty on the position and on the velocity times mass must be larger than some fundamental constant of nature that's called the Planck constant h bar. There is the numerical value, probably doesn't mean much to you. So to illustrate what that actually means, I'll give you a little example. Take a tennis ball that goes at, let's say, 30 meters per second, 100 kilometers an hour. And so it's got a mass of about 50 grams. The Heisenberg uncertainty principle tells you that if you try to measure the velocity of that tennis ball to within 10 to the minus 16 meter per second, so to a millionth of a billionth fractional precision, you need to have an uncertainty on its position which is less than the size of a proton. So what that means is, who cares, right? A tennis ball is not a quantum object because the Heisenberg uncertainty principle has no relevance to its behavior and dynamics. Take instead an electron, which is much, much lighter, of course. You see the mass goes in there in that formula. For the same speed, if you try to measure its velocity to 30% precision, you already kick him. You need to have an uncertainty on where it is by about 10 microns, which is significant. I mean, it's many, many times more than the size of the electron itself. So basically, you don't know where it is. Neither do you know how fast it goes. So what it means is that you need to start describing objects at this scale with different laws and with different also, mindsets. So instead of saying the electron has a trajectory like a tennis ball that goes from one chord to the other, you need to talk about essentially a wave of probability that evolves in time that tells you where are you most likely to see this electron and where is it most likely to be going. And this is just the way it goes at the microscopic level. But actually, this is a bit of an outdated description of what the quantum world actually is, as I'll say in a minute. Now, one important aspect of the uncertainty principle is that because particles like electrons cannot be localized to very small regions, they spread out in space. So if you imagine shooting an electron through a screen that has two slits, this electron is spread out, and so it actually passes through both slits. And if you try and look at the back of the slit where it ends up, you will find an interference pattern that is the same thing you would expect in waves. You can do it at home in your bathtub. You take a cardboard and cut two slits, fill the bathtub, and drop a pebble on the one side of the slit. And you'll see that there are these rings of waves. And in the back, they interfere. They make these patterns of maxima and minima. And an electron will do just the same. This is because of the uncertainty principle, in fact. And what that means is that the electron really passes through both slits. So as we say, is in a quantum superposition of being in both places. Now, this is where, everybody goes, oh, but this is weird and spooky and so on. But, I'll tell you that that's not true. Anyway, so before I get there, what's in between? So, okay, the electron is a quantum particle, the tennis ball is not. But, there's a big size gap between the electron and the tennis ball. Where is the boundary? At what point does the quantum world stop? So this is a very interesting, topic these days, because there are people who have been playing that kind of interference two-slit experiments with particles much larger than electrons. This is, as far as I know, the biggest one that's been seen to behave like a wave, so to be in a superposition of going through both slits. It's carbon 168, hydrogen 94, fluorine 152. I don't know if it's got a name. It probably does. But anyway, it's a complicated big molecule. Okay? This thing has been seen to go through both slits. Now, the nice thing about it is that this thing is small. Of course, it's still a molecule. But, if you want to think forward a little bit, this thing is the smallest virus. It's called the porcine circovirus. It's a virus that affects pigs. And it's about to scale. So it's bigger than the molecule, but not a lot bigger. So biologists kind of don't agree whether a virus is a living creature or not. They probably think it's not. But let me just entertain the argument that a virus is on its way to being a living creature. And so we are not a long way away from being able to put a almost living creature in a quantum superposition of being in two places at the same time. That's cool, right? Now, let's go a little bit bigger. This is an electronic circuit. It's a loop of metal that is actually a superconducting metal, so it carries current without dissipation. And in this circuit, already nearly 15 years ago, people have demonstrated you can have an electrical current, a sizable electrical current, that is in a quantum superposition of flowing clockwise and counterclockwise. It doesn't mean it's zero. It's a superposition of flowing clockwise and counterclockwise. But this object is big. This is 10 microns across. So on that scale, that's a human hair. You can basically see this thing on the naked eye. So the old argument that quantum is microscopic and classical is macroscopic is actually not really holding water anymore. And the job of people like me and many of the people in the room who are participating in this Pink Qubit conference this week is to actually make increasingly large and complex quantum systems that we can then operate to have new functionalities. So we're pushing the quantum to classical boundary all the way up. Now, let me get back to the issue of whether superposition is weird or not. What I find really compelling and satisfying, both intellectually and practically, about quantum theory is that it really accounts for symmetries and discontinuities very well. Okay? So let's say you have two protons, two positive charges. Okay? They're identical. And then you have an electron, it's a negative charge. So again, oversimplifying, you'd imagine the electron orbits around the proton, but there's two of them. They're indistinguishable. So your classical, supposedly intuitive intuition will tell you, well, it would orbit either around the left proton or the right proton. Now, how does that make sense? Why would it choose the left or the right? There is nothing to make it do that. It's actually much more intuitive once you get used to it to say, well, the system is symmetric, it spreads out across both. It has no reason to choose, right? That's why I don't buy the whole counterintuitive thing about quantum mechanics. This is actually much more intuitive than imagining there is some strange reason, which actually isn't there, why it chooses one or the other. And by the way, so this is, like a cartoon with the electron going around the protons like the moon around the Earth. In reality, you have to think of this as a wave of probability that's spread out across the two charges, okay? Now, can you see these things? I mean, all these are cartoons. But actually, in the last 20 years or more, in fact, people have developed instruments that use quantum effects themselves to probe the wave of probability of electrons. This picture here is from more than 20 years ago. It's the image done with a scanning tunneling microscope of the density of electrons on the surface of a piece of copper with iron atoms placed in a ring. And you see that this ring, they call it a quantum corral, kind of makes the electron create a wave of probability within the ring. And this can be seen. You can measure that. Okay? This is new. This didn't exist, in the days of Feynman and Heisenberg and Einstein and whoever. These are new tools that we are creating to actually gain access and therefore intuition for the quantum world that we never had before. All right, now let's move to our favorite system, the spin. So an electron has a charge, a negative charge, but it also has a spin. And most nuclei also have a spin. A spin is an intrinsic magnetic dipole. You can think of it as the microscopic version of the needle of a compass. So it creates, a magnetic field kind of like the Earth does, but of course it's very, very, very small. Now, can we see a spin? Well, you can see a lot of spins if you ever have the misfortune of having to get a magnetic resonance scan because there's something wrong with you. I don't wish you that, but if you ever do, you'll get these beautiful images of your insides without any harm done to you. And what this is the signal of the coherent quantum precession of the proton spins inside basically the water molecules or some other molecules inside your body. And you can create a three-dimensional, in fact, scan of your body using the signal from the trillions and quadrillions of spins that are inside our body. So that's nice and useful, but what about one spin? Can you see one spin? Well, we can. So this is one of the things that, again, are the topic of the conference that give the excuse for this public lecture. And this is a device that was made in my laboratory. We have sort of pioneered some of these things. This is a silicon electronic device. Think of it as an artisan silicon transistor where we place a single phosphorus atom. The phosphorus has one more positive charge compared to silicon. So when you replace a silicon atom with a phosphorus atom, that extra positive charge attracts an extra electron. So it behaves a little bit like hydrogen, but it's inside a functional electronic device. And this functional electronic device can talk to the spin. So this is a movie that was made actually by a student of the College of Fine Arts at UNSW a few years ago to illustrate the thing. So you've seen this is the actual image of the device seen from above. The colored things are basically metallic electrodes. And now imagine you kind of go down and dig inside the silicon chip and look up towards the ceiling. What you would see is something like this. The blue spheres are the electrons that are accumulated under these electrodes. And then we tune the device such that there is a puddle of about 100 electrons that's isolated there. This makes the transistor be very, very, very sensitive to movements in the charge in its vicinity. And then the little red sphere I've drawn there is the nucleus of the phosphorus. The nucleus itself has a spin, okay? And I've drawn it pointing kind of down that way. So the way you observe the spin of both the electron and the nucleus, in fact, is you suck an electron from that island and you put it on the phosphorus atom. Then you irradiate it with microwaves at a specific frequency such that the spin rotates. And when it rotates from down to up, it then escapes back into the island. And when it does so, it turns on the current in the transistor. You can measure the current. It's an electronic device. Then at some point, another electron spin down will go back onto the atom. And then you can try a different frequency, which is the one that the electron would respond to if the nucleus was pointing the other way. In this particular animation, we have shown that the nucleus doesn't change, so the electron doesn't respond, and so there is no current. So this is a long story. I want to show you what it actually looks like in real life. This is just a video taken, with my mobile phone in the lab. This is basically the screen of the oscilloscope that is connected to this little transistor. So what you see there is the current through the transistor. So every time you see a spike of current, you have seen an electron spin, just one electron spin, pointing up. And you see there are periods like this when there's a lot of these blips. So the electron kind of comes up and down all the time, and then it stops. What we have done there, we have turned the nucleus the other way. So whether or not the electron responds depends on the direction of the nucleus. So now I want you to ponder on this for a minute. What you're seeing here with your eyes, there's no trick, no photoshopping, it's just what you would see if you came to the lab, is the real-time, real-life observation of the quantum state of a single electron as well as the quantum state of a single nucleus and quantum jumps of the nucleus from one side to the other. Okay? This is the kind of things that 20 years ago when I was a student, my quantum mechanics lecturer said, well, you can never do that. You just should never think of watching a single quantum system. It can't be done. In fact, it was only in 2012, 5 years ago, that 2 people got the Nobel Prize for being the first one to actually make this happen with atoms in vacuum chambers. Okay? So this is, for me and for my students, is our daily bread. But 20 years ago, most people didn't even believe it was even in principle possible. So this is another luminary and founding father of quantum mechanics. This is something he actually said. He wrote it in a paper. If we have to go on with these damn quantum jumps, then I'm sorry that I ever got involved in quantum theory. We just saw them, right? Right? The level of contact and interaction we have with the quantum world has completely changed in the last 20 years. Now, there's the next beast, is entanglement. This is the thing that Einstein had troubles with, okay? So, again, this comes from a very fundamental, interaction in nature. It's called the exchange interaction. It's basically a form of interaction between charges and spins. It's actually based on charge, where the spins want to point in opposite direction. But there is no preferential direction. I mean, the universe is, isotropic. It doesn't care if they're opposite this way or opposite that way or opposite that way. So now tell me intuitively, which way do you think spin left points and spin right points? They don't point anywhere. All they do is they point opposite. That is the fundamental logical state of those two spins, interacting through this interaction that makes them be opposite. That's all there is to it. So here I'm having, of course, trouble drawing this. I cannot draw two arrows that don't point anywhere but point the opposite. That's because I'm using a classical projector and a classical screen, so I've kind of made this sort of animation where they disappear into each other, and they only exist essentially in relation with each other. Now, is this weird? Is this strange? Is this some incredible thing that nobody ever thought would ever be possible? Well, you're made of this stuff. That's a water molecule. Every bond between the oxygen and the hydrogen in that molecule contains two spins that are exactly in that entangled state. There's absolutely nothing strange about it. You are made out of this thing. Now, can we see this? Again, can we see it? Well, we can't. Well, we can deduce it, and that's a different matter. But one very interesting hypothesis, it's really a hypothesis, it's very hard to prove it, beyond doubt, but there is some indication that there are some birds called the European robin, very cute little birds, who can actually essentially see the entanglement. What does that mean? So in the eyes of this bird, there is, in the retina of the bird, there is a receptor that has a pair of electrons that are kind of loosely bound, and they are in this entangled spin state. So they point opposite, but they don't point anywhere. By the way, the reason why this entangled state is so common and widespread is because it's really the lowest energy state. That's how the electrons want to be. If they weren't that way, they just wouldn't bind, okay? The chemical bond relies on that. So then this bird is migrating to, from Northern Europe down to Africa to get warmer weathers. And how does it fly? How does it know where to go? It follows the Earth's magnetic field. And people have been wondering, how do they know where to fly? So the hypothesis, and there is some evidence for it, is that what happens is that when light hits the receptor in the eye of this bird, the energy imparted by the photons, by the quanta of light, separates these entangled spins, and once they're separated, they start precessing in the Earth's magnetic field. And then after a while, if they remain entangled, they recombine, and the recombination gives back to the optical nerve of the bird the energy that was originally imparted by the photon. Now imagine the bird turns its head the other way, and another photon hits. Now these spins turn a different way because they're turning around a different magnetic field direction, and they may end up parallel. Now they can't go back to their orbital anymore. So the bird doesn't get the stimulus. So the way you kind of imagine this bird navigating is that it sees bright when it can recreate this entangled pair of electrons, and it sees dark when it can't. And dark and bright tell it which way to fly. So poetically speaking, you can say this bird has eyes that can see the quantum entanglement, right? That's cool, isn't it? Okay, so this is all I wanted to say about this part one and, weirdness and spookiness. I hope I've somewhat convinced you that these things, they're great and cool, but they're not necessarily weird and spooky. This stuff happens everywhere, and it is at the basis of a lot of processes, right? So first thing, uncertainty. The uncertainty principle is a fundamental law of nature that governs the world. Superposition, when you have a particle that can be in two places at the same time and has no reason to choose one over the other, it doesn't, obviously. Entanglement, when you have two particles that interact in a way that just makes them relate to each other without having a relation to the rest of the world, they are in this special state where they don't have a state of their own, they're just in relation to each other. And observation. We can now see a lot of these things that we could never see before until about 20 years ago. This is new. This is the advantage we have over the founding fathers of quantum mechanics. They didn't have the sort of, artificial eyes that we have created to watch the quantum world. All right, so how do we use this? So let's move to part two, which is applications. The king of quantum applications is, of course, the quantum computer. So before I get into what actually a quantum computer is, I'll give you a little hint of what, a reminder of what a classical computer is. This is a very old image of one of the very early chips. If I took a newer one, you would be hard-pressed to tell even what's in there. So a digital computer, encodes and elaborates information in digital form. So it's all zeros and ones, binary code. So for example, if you want to calculate 3 times 5, you will write 3 as 0011 and 5 as 0101. And inside this electronic circuit, there are things that happen, and what comes out at the other end is 1111, which is the binary code for 15. So 3 times 5 is 15, great. Now, these zeros and ones have a physical reality to them. Information is physical. This was the motto of the greatest Rolf Landauer. So when I say 0 and 1 inside of a classical computer, what that means is that in there are some physical objects, in this case silicon transistors, and the 0 and 1 is a physical quantity related to these objects. Is the voltage across the transistor, is a high voltage or a low voltage, right? That's what 0 and 1 actually means. It's a physical object. Now, can we do the same with quantum objects? So I showed you before that if you take, for example, 2 protons and 1 electron, you can have the electron orbit in the left proton, and you could call that the 0, or orbit in the right proton, and you could call that the 1. It's a binary choice. You can encode binary information there. But because the electron is a quantum particle, it can also be in a quantum superposition of 0 and 1, which a classical transistor cannot be. But it's completely natural and logical in these particles. Another option is the spin. The spin has 2 basic states, spin down and spin up. So you can call spin down the 0, spin up the 1. And again, because the spin is a quantum object, it can be in a quantum superposition of 0 and 1. Now, what do you win by doing this? So let's have a look at how you would, write classical digital code. So this is, for example, if you have 3 bits of classical information, you can write all the numbers from 000, 001, 010, down to 111. It's basically from 0 to 7. And you need 3 bits of information to decide which one of the 8 possibilities you have encoded in your machine. Now, in a quantum computer, the same thing holds, so you can make all the combinations of zeros and ones, but you can also make the quantum superposition of all those combinations of zeros and ones. And many of them are, in fact, highly entangled states. So now, to specify in which precise quantum state my 3 particles, imagine 3 spins, are actually finding themselves, I need to give you the exact weight of all the 8 branches of the superposition. So that's actually 8 numbers I need to give you to specify the quantum state of 3 spins. Whereas before, I just had 3 bits. I had, B1, B2, B3, and now I've got from C0 to C7, 8 numbers. So in general, with 8 numbers needed for 3 qubits, if you have n qubits, you need 2 to the power n numbers. So 4 qubits, 16 numbers, 5 qubits, 32 numbers, and so on. So this is dangerous, right? Because, for example, as far as we know, more or less, there are this many particles in the universe, that 1 with 90 zeros after that. So it's 10 to the power 90. And 10 to the power 90 is about the same as 2 to the power 300. So that means that if I have 300 fully entangled quantum bits, I need as many numbers to describe them as there are particles in the universe. Okay? So this is quite spectacular computing power, but you need to learn how to use it, and that's where the challenge is. So there is a worldwide race nowadays to demonstrate what's called quantum advantage in its most politically correct term, which is basically showing a calculation that just cannot be done on a classical computer. So let's forget about the 300 and the atoms in the universe. Let's talk about something a bit more tangible. So if you have, let's say, 50 qubits, you need 2 to the power 50, which is 10 to the power 15 numbers. So that's a petabyte. I don't know if you ever heard the word petabyte. You probably heard terabyte. This is a terabyte hard drive, right? That's 10 to the 12. A petabyte is 1,000 terabytes. So basically, to describe the state of 50 qubits, you need a stack of 1,000 of these, which you can kind of imagine fit on this table, fine. If you had 70, you get 2 to the 70, which is 10 to the 21, and that's a zettabyte. So that would be a billion terabytes. So now it's a billion of these. Where do you put them? It turns out that zettabyte is about as much data as there is on Earth now. Okay? Everywhere. It's about a zettabyte. So if you can run a meaningful quantum calculation on a computer that has as many qubits as this, you can, defensively claim that you have done something that just cannot be done in any classical setting. Okay? And it's not like you say, well, okay, but then, the hard drives are getting always better. Last week I just bought a 2 terabyte one that cost half this one. It doesn't matter, because if you had 1 qubit, then you need to double all the data in the world. So it really doesn't buy you very much. Okay? And so there are many laboratories and companies racing for this. Google is particularly famous for being at the forefront of this. This is a 9-qubit device. They have been talking about their 49-qubit device being kind of around the corner. We're all very excited to see when that happens. But they're not the only ones. There are multiple large players in this field racing towards demonstrating this quantum advantage. Okay? All right, so now I want to give you an example of application. So let's say you've made this big quantum computer. What is it good for? And there's one particular experiment that just got published a couple of weeks ago from IBM, and it sort of inspired me to try and give it's oversimplified, okay? Don't take it literally, but just to give you a sense of the complexity of certain problems where a quantum computer makes something from insolvable to solvable, okay? So let's say you got a 6-pack of eggs and 2 eggs. In how many different ways can you place 2 eggs in a 6-pack? So for the first one, you got 6 options, right? The 6 empty spots. Then for the second one, you got only 5 options because 1 is taken. So that would be 6 times 5, but then we're going to assume that the eggs are indistinguishable, so you actually have to divide by 2 because, the eggs are the same. So, if you swap them, it's still the same combination. So basically, there's 15 ways to arrange 2 eggs in a 6-pack. Okay? Is this weird or spooky or counterintuitive or something? No, it's just eggs in a pack. Okay? All right, let's double the size of the problem. 4 eggs in a 12-pack. So now you've got 12 options for the first one, 11 for the second, 10 for the third, 9 for the fourth. But you have to divide by all the number of permutation of 4 eggs, which is 4 times 3 times 2. So that works out to 495. Notice what happened. I mean, you went from 15 to 495 just by doubling the size. This thing goes up very quickly. Okay? It's just combinatorials. So the way I kind of want to portray this, and really don't take it too literally, but to some extent it works, is imagine that the eggs are the electrons and the atomic orbitals are the boxes. Okay? So the problem of understanding atomic and molecular physics and chemistry is basically the problem of understanding how to put electrons in orbitals in the most energy convenient way. So the difference with the eggs is that, other than the aesthetics, it doesn't really matter where you put the eggs in a half-empty pack. Whereas for electrons on an atom or in a molecule, it does matter because electrons have charges, they interact with each other. So the whole problem is to find out what is the best configuration for all these electrons. And so if you really want to do it right, you have to try all the combinations and calculate all the interaction between all the possible combinations of, eggs in the pack, electrons in the orbits. So this is, as I said, an experiment that's just been published a few weeks ago. It's the quantum simulation of beryllium hydride. Beryllium hydride is 1 beryllium, 2 hydrogen. Beryllium is a very light atom. It's element number 4. So it's got 4 electrons. Hydrogens have 1 each, so there's 6 electrons in there. So it's a fairly small problem. But if you were to actually properly, not just eggs in a box, but all the quantum mechanical prescriptions, try to describe how many different configurations there are for these electrons in this very simple molecule, there's 40,000. And then you have to write a matrix that is a 40,000 by 40,000 matrix and calculate things about that matrix that will tell you what is the most favorable configurations of the electrons in there. This is actually a really hard problem, just for a simple molecule like this. On a quantum computer, this has been done at IBM, what you can do is to basically map a quantum bit with, an electron in an orbital. I won't go into the details of how exactly you do that. It's not that trivial, but basically they've shown that they can, reproduce and simulate the energies of all the, best configurations of the electrons in this very simple molecule on a 6-qubit quantum computer. So remember, the alternative is a 40,000 by 40,000 matrix. And that's for a small things like this. Okay? So now let's up the ante a little bit. This is a photo courtesy my friend Emily, who works at my favorite cafe in Newtown. I'll tell you later what it is if you ask. So of course there they run through a lot of eggs. And so this is a 30 pack with 20 eggs in it. So how many different combinations of egg position can you make in this 20 eggs in a 30 pack? Well, it's 30 by 29, down to 11. And then you divide by all the permutation of 20 eggs, so 20 times 19, times 2. How much is that? What do you think? It's about 30 million. So don't try that in the cafe. There's 30 million different ways to arrange those 20 eggs in the pack. Right? So now I understand what the problem is, right? So imagine you want to do something that actually is important, not beryllium hydride, but something that actually has an impact on humanity, such as this thing. This is penicillin. Now, there's probably at least 100 electrons in there, so that's even way more than the 20 eggs in a 30 pack. This thing is just completely beyond hope. Right? Whereas on a quantum computer with a sufficient number of quantum bits, you can program it to find by itself the configuration of a molecule like this. And this is a molecule we already know, but of course what we want to do is to discover new molecules, new drugs, new medicines, new materials. And the reason why it's so hard to do it nowadays is because you can't just program it on a computer and say, oh, tell me what is the reaction product of molecule A and molecule B, and does it make, let's say, anti-cancer drug? You just can't do that. It's not a matter, oh, it's slow or it's difficult. You just can't do that. So this is what we hope a quantum computer will be able to do. Another example, which is quite famous these days in our field, is the nitrogen fixation. Basically, the reason why we, as a humanity are as many as we are and we can sustain ourselves is because of our ability to produce ammonia for fertilizers. If we didn't have ammonia, we could not have as much agriculture as we have. But the reaction to produce ammonia is fantastically inefficient. You need to heat up the reagents to very high temperature, and it's really slow. And we haven't found a better way. This was invented in the 1930s by Fritz Haber, and we still haven't found a better way. I just learned yesterday from Ted White, who is from Google. He was telling me that apparently there is a bacteria that synthesizes ammonia in its guts, so at room temperature. So if we could figure out how to do it at room temperature without heating to, I think it's 650 degrees you need for the Haber reaction, we would save about 2% of the world energy. This reaction, the production of ammonia, consumes 2% of the entire energy consumption of the world. And it's so inefficient. It's because we don't have the ability to solve the quantum mechanical problem that it is predicting and designing a chemical reaction. Another very interesting application is database search. You can use the fact that you can create a large superposition of inputs to speed up the time it takes you to find an element in, for example, an unsorted database. I don't have the whole story here in the animation. I'm going to do a little bit of shameless self-promotion. There is a series of videos on YouTube that I've produced, and one of them is about how to do quantum search on what's called the Grover algorithm. All right, I just want to say one more thing about quantum computers, again, because there's a lot of misconception in people's minds. Is people say, okay, when am I going to have one in my bedroom? Can I put a quantum computer in my pocket? And will it play, some video game better? Those are all, really not very constructive questions, but there is a simple answer to them. So for video games, it probably doesn't matter, although I don't know, maybe it will make an impact. What's really the point of quantum computers is that I think of it as a jet plane versus a car. You should not think of a quantum computer as a faster computer. It's a different machine. I mean, a jet plane, yes, it's faster than a car, but it's not the point. It's something that does a task that a car cannot do, like flying, right? Anyway, so these are some examples of, quantum hardware. So the one on the left is the silicon chip that we make in my team at UNSW. The one in the middle is a superconductor quantum chip from IBM. The one on the right is an ion trap. That's also a very successful way to make quantum bits. You basically suspend ions in vacuum in a vacuum chamber. So the silicon chip is very small, it's a millimeter across. The superconductor chip is a bit bigger. The ion trap is, even a bit bigger. But those are all, still fairly small. But of course, that's only, the quantum bits themselves. In reality, if you want to operate something like that, you need a big refrigerator that cools it down to nearly absolute zero temperature. And that thing is like, 3 by 2 meter, 2.5 meter tall, and it's got, 20 kilowatts of cooling, cooling water needed and a big compressor. So that does not fit in your pocket and probably also not in your room. Same with the ion traps. I mean, the trap is small, but you got a gigantic optical table full of lenses and lasers and other stuff to use them. So this is what confuses people. They think, oh, but then I can never have one, for general purpose for people. But that's because people think that a classical computer is this. That's complete nonsense. That's not a classical computer. This is a classical computer. Nowadays, the vast majority of the calculations you actually do don't happen in your phone or in your laptop. They happen somewhere on a server on the cloud. So there's a big room full of these blades, full of processors that you connect to remotely. That's where most of your actual computation takes place already today. So on that scale, my big refrigerator is about that big. You won't even know. Right? So the way we envisage using quantum computers in the future is to have, data centers where there was going to be a quantum room and you connect to it remotely, right? So no big deal. Regarding low temperatures, because as was correctly pointed out, I come from the birthplace of low temperature physics, it's very close to my heart. The achievement of low temperatures as needed to operate these quantum chips is probably one of the most demonstrable, tangible demonstrations of human intellect and ingenuity, in particular in doing something that nature does not do. Okay? So if you go to the furthest, most remote place in empty interstellar space, the temperature there is cold, but actually not that cold. It's 2.7 degrees above absolute zero. I learned a few years ago that there's a colder place than that. There is a nebula that is actually expanding, so it's about 1.4 Kelvin. But still, that's about the coldest place we know. Whereas in our labs, we achieve routinely 0.007 degrees above absolute zero. So I remember an old professor of low temperature physics saying, kind of a speculative way, if you could make a map of the universe, a temperature map of the universe, so if you knew the temperature everywhere, to a precision of, 10 centimeters, and you found temperatures like that, so much below 1 Kelvin, you would know there is intelligence there. Because nature doesn't do that. You need intelligence to create these temperatures. Okay? So, little self-congratulation again. All right, next application. This is also very, very sexy and actually really useful already these days. Is quantum sensing. So one thing that's very, it's already making great progress is using spins as extremely sensitive detectors of their environment at the nanometer scale. There is a particular type of spin, which is a color-centering diamond. I mean, you're used to think as, the good diamonds are perfectly transparent. But in fact, if you get a slightly less good diamond, it will have a little bit of a, color. And that's because there can be defects in the diamond crystal and impurity. And those impurities emit light. Many of them also have a spin associated with them. And so you can actually, by looking at the way these impurities blink and like emit light, you can actually tell the direction of their spin. It's an amazing thing, and it works at room temperature. So people already for many years have been developing this technique where you take, for example, a nanoscale diamond, a tiny, tiny speck of diamond that has one of these impurities in there, and you put it next to something you want to feel. This is an example of a complicated magnetic material that has a strange magnetic texture. And then this spin will start to evolve in the magnetic field of that environment you've put it in, and you can then measure it by the light it scatters. This is fantastic. You can scan it at the nanometer scale, even at room temperature, which means people have been looking actually at living cells. This is the HeLa cell. It's a very popular cell in biology. It's a cancer cell of a woman. I forgot her full name. It's a Helen La something. Yeah, Henrietta La. And so this culture is still there. It still propagates. And so people have put these nanodiamonds inside the cell. And then they illuminate it, and they track the fluorescence of these nanodiamond impurities, and they can follow how the diamond moves around the cell, and they can also tell something about the magnetic environment inside the cell without actually killing it. This is quantum sensing. It's something that, you know, was unthinkable until a few years ago. All right, and then another favorite of the spooky sensationalist media is quantum teleportation. Okay, so you've all seen some movies where people presume teleport you somewhere. What I'm going to talk about is actual quantum teleportation, not of objects, but of information. This is something that already exists. It's been done again about 20 years ago. So it's based upon the idea that, imagine there is one person, let's call it Alice, who has a bit of information she wants to send to Bob. But she's concerned that someone will tap the connection and you know, eavesdrop the line. Now, imagine that Alice and Bob can share a pair of entangled particles. So let's say a pair of spins. And again, this is my attempt to show a pair of entangled spins. So they are just related to each other. They point opposite, but they don't point anywhere. Okay? So just remember, they're always in opposite direction, but they don't point anywhere. Now, how do you transmit that bit of information, which is, in this case, is a 1, from Alice to Bob in an absolutely secure way? So what you do is you separate that pair of entangled spins. One goes to Bob, one goes to Alice. Then what Alice does is she measures, it's called a parity. Basically, she measures whether the spin she received from that entangled pair is opposite or parallel to the one she's got. Okay? So if she sees that, for example, it's parallel, so it's the same, first of all, instantly, the one on the other side will take the opposite direction as the one that's been measured. And then, but the way this happens is random. You cannot predict whether it will turn the same or the opposite. But whatever happened, Bob has a spin that is perfectly correlated to what happened on the left-hand side. But Bob, at this moment, doesn't have any information yet. He just got a random number. So then Alice needs to take the phone and call Bob and say, hey, Bob, my spins are the same. Now, with that information, Bob can figure out what was the bit of information that Alice wanted to send, because he knows that his spin is the opposite of what Alice has, and if what Alice has is the same as what she wanted to send, then Bob should take the opposite of what he's got. So if he's got a down, it means Alice wanted to send a 1. It could have gone the other way. So you could have started with your entangled spins, separate them out, Alice measures them, and she finds them opposite. So now Bob has got a spin up. Alice picks up the phone, says, hey, Bob, they're the opposite. And Bob knows, well, if they are the opposite to you, it means what I've got is what you wanted to send me, so it's a 1. So the bit of information from Alice has been teleported to Bob. The reason why this is absolutely secure is because if you try to, for example, catch the spins as you separate them out, there's no information in there, right? So they're just completely, they're opposite, but they're random. They don't have a state of their own. And then, if you actually tap the telephone between Alice and Bob, you say, okay, it's opposite. Opposite to what? It doesn't tell you anything, right? So all you see from the outside, unless you are Alice and Bob and possess the original bit and the other part of the entangled pair, is random numbers. The other thing that happens here, and it confuses a lot of people, they say, oh, but Einstein didn't believe this, the spooky action at a distance, it violates relativity. No, it doesn't, because until Alice makes the phone call, Bob has not gained any information. Yes, there is an instantaneous action on Bob's spin when Alice makes the measurement, but that action just creates a random number. It does not transmit any information. The information only is transmitted when Alice makes the phone call, which of course is limited by the speed of light. Okay? This thing is not science fiction. This thing already happens, and I'm making a little bit of Australian advertising here. There's a company in Canberra, it's a spin-off of Australian National University called Quintessence Lab, that already produces and sells technology solutions for cryptography, random number generation, you also get that from this, and quantum communications. So you often hear, in the popular media that quantum computers will, break encryption and make our data unsafe. That is so far down the track, whereas quantum security is already there. So the degree of advancement of quantum-enabled data security is way up compared to the potential ability of quantum computers to actually crack codes. So this gives me a kind of nice intro into the business side of things. So I already told you about Quintessence Labs down in Canberra. Now, who in the world at the business level cares about this? This is actually an old little slide, and there's many more companies than this. It's just a little example of people worldwide. So Google is looking at making artificial intelligence and optimization problems. Lockheed Martin is looking at actually debugging classical code. Alibaba in China, they want to have, of course, communication security for e-commerce. NEC and Fujitsu, again, long-distance safe communication. So this is worldwide. What about Australia? So in Australia, we've got Telstra that is looking at real-time network traffic management and data security, and the Commonwealth Bank that is interested in using quantum computer for complex financial markets analysis. And together with us at UNSW and with the support of the federal and state government, we have created a new company called Silicon Quantum Computing, which is a consortium that has the goal of developing a practical prototype of silicon quantum computers based on the research that we have done in the last 20 years nearly. On this very place at Sydney University, there is a node of Microsoft Station Q. So Microsoft has a big investment worldwide, but with a node at Sydney University to build topological quantum computers. I'm not going to go into the details of what that is unless you ask me really nicely. It's a big, complicated, fascinating way to build quantum computers. And then also in Australia, we have a branch of QBranch, which is a company that is looking at using quantum computers for data analytics and machine learning. So there is actually a nearly exponential explosion of investment and actual business interest in quantum technologies. This is the next technology revolution. Now, my next and last bit of shameless self-promotion, quantum businesses need quantum engineers. Okay? So with my colleague Jared Pla and others in our school, we are developing, in fact, a stream of quantum engineering within the School of Electrical Engineering and Telecommunication at UNSW to teach the quantum aspects of engineering that will be needed for the next generation of engineers to actually partake and contribute to the quantum technology revolution. So with this, I'm finished. I'm going to just give you a little reminder of what the key technologies are. So this part number 2 highlights quantum computers, of course, quantum sensors, and quantum communications. And all of this is new. All of this. This is all stuff that came up in the next 20 years. And we have barely started. So stay tuned and get engaged. Thank you.